Hi, welcome back to another episode of Algebra in Words, the video series on YouTube. What we're going to look at in this video is radicals and how to start simplifying radicals. Everything that we go over today, you can follow along with in my books, Algebra in Words 1 and 2. And if you want to follow along with any of it in written form, you can find it in Algebra in Words 1 starting on page 127. And starting on page 58 in Algebra in Words 2, where we look at some more advanced topics of radicals with regards to radicals. Also, you can get some more background on radicals from my previous videos in episodes 103 and 109. So anyway, let's get started. What I have on the board is just a few basic notes of some background of radicals. So the point here is going to be to learn how to simplify and evaluate radicals. In this case, simple radicals, and we'll get more advanced in future episodes. But this will lay the foundation for that. So what I have here is a basic explanation of radicals. You have the root and you have the radicand, which is the numbers or the symbols under the symbol, under the radical symbol. And what you need to know is that in one situation, when you have the base and the root and the exponent of the base are the same, it equals the base. Also, this form is interchangeable with this form, and in this form, if you notice, the power or the exponent is outside of the parentheses of the entire root, which is inside the parentheses. So this form and this form are basically interchangeable, and as long as, again, the point is when the root is the same as the exponent, it equals the base, and I have that designated as b, just for exemplary purposes here. So I have a couple little examples to show this. Let's look at this one, where we have root 7 of x to the 7th, and it equals the base x, because the root and the exponent are both 7, they're the same. Not much more to say about it. And it could get a little more complicated from there. But then let's look at this example. And in this example, notice that there's a couple things to notice. One is there's no number written in for the root, and whenever there's not, that's for you to assume that it's root 2, the square root. So we have root 2, and then also in this form, I have my exponent outside the parentheses. Notice that, which is fine. The root and the exponent are the same. And it's going to ultimately equal b, but there's one more thing to know about this. In this example, the root was an odd root, and so it just equals the base. But in this example, the square root, or root 2, is an even root. And when you have an even root, the intermediate step to know is that the solution is the absolute value of the radicand. And just to add some clarity to that, why is that? Well, it's because if you were to further break down the absolute value, what could b be? It would have to be plus or minus whatever b is. And why is that? Because if you think of it in reverse, if you were to take b and apply the power to it, then it would ultimately equal whatever is under the radical. So for example, let's say that you had the square root of 4. The square root of 4 would equal plus or minus 2. Because if you were to go to in the reverse, positive 2 squared equals radicand 4. Or negative 2 squared would also equal radicand 4, because a negative times a negative equals a positive. This only applies to even roots. Now, likewise with even roots, there's one other caveat. What happens when you have an even root of a negative radicand? Well, that's going to equal not a real number. And basically, the reason behind that is if you were to take this and apply the power to it to go in reverse, you could not apply an even power to a base and arrive at a negative number, because that's impossible. Even powers only would result in a positive number. I get a little bit more into this, which I'm sure you may know would equal, we work with as imaginary numbers. We'll get into that in a few videos later. But for now, what you need to know is when you have an even root of a negative radicand, for now say, does not equal a real number. So what I'm going to do next is put a few examples on the board and we're going to evaluate those. I have a few problems up on the board that we're going to go over. And I have the answers there, but there's not much to work out, so there's not really much to show except to explain how we arrive at the answer. So let's look at the first one. The first one is the square root of 121. And the answer is plus or minus 11. And how could you check that? You could take 11 squared and it will give you 121. Or you could do negative 11 squared with negative inside the parentheses and still get 121. Now let's look at this one next. It is the square root of, now a decimal, 0.64. And the answer is 0.8. Now, let me just briefly explain how you evaluate radicals that have a decimal. First of all, what I want you to think of is, I want you to recognize that 64, if there were no decimal, would be a perfect square. For example, the square root of 64 is 8. Okay, but, so the first thing is to think of it without the decimal. The next thing is to think of what the answer would be without the decimal. It would be 8. Now you're going to do this. Starting from the right side, count the number of decimal points there are. There's 2. 1, 2. Alright? And since it's dealing with the root 2, then what you're going to do is take the number of decimal places divided by the root, and that's going to give you a number. In this case, 1. You're going to apply that number of decimal places to the answer and move it that many decimal places. So since 2 decimal places, 2, divided by root 2 is 1 decimal place, then starting from 8, we're going to move 1 decimal place from the right to the left, 1, and that's how we get 0.8. And you could apply that to any radical that's dealing with that involves a decimal, assuming that it's a perfect power type of root. Okay, let's look at the next one. It's the square root of 9 over 49. Now, this is to exemplify taking the radical of a fraction. Now, in this case, coincidentally, the numerator and the denominator are both perfect squares as well. So we just apply the root to the top. Square root of 9 is 3. And the bottom, the square root of 49, is 7. And since it's an even root, because it's root 2, the square root, we have to apply plus or minus 3/7. Let's look at the next one. And this one takes it up to another level because now, unlike the previous ones, we're dealing with a radicand that involves a binomial. And if you notice, the binomial is squared. If you remember from a couple minutes ago in the video where I showed you the little explanation, you might want to rewind to that. And remember when I said when the root is the same as the power of the base, it equals the base. And that exactly applies here. Even though the base happens to be a polynomial, in this case a binomial, it could have as many terms as possible. But again, this is just to exemplify that when the root is the same as the power of the base, it equals the base. And that's what that exemplifies here. There's nothing else to it. Let's look at the next one. The cube root of 64 equals 4, because 4 cubed equals 64. It's only positive 4 because it's an odd root, and therefore we do not have to give the answer as plus or minus when we have an odd root. And finally, of these 6 examples, I have root 5 of negative 1. And that's going to equal just negative 1. And again, why does it equal negative 1? Because it's an odd root. And we can take the odd root of a negative radicand, and it equals negative 1. How would you test that? Take negative 1, raise it to the power of 5, and you would arrive back at negative 1. I have another problem up on the board. The cube root of 2x in parentheses raised to the power of 6. Now, this one's a little different because unlike the ones we just looked at, where I told you that if the root and the power are the same, it equals the base. But in this case, the root and the power are not the same. One's 3, one's 2. So I'm going to show you how to do that. In short, what you want to think of is the power divided by the root, just simple division, and then apply that number as the exponent to the base. So again, think of 6 divided by 3. The power divided by the root. I'm not going to write that, but it's 2. And apply that to the base. So that's where the 2 came from. 6 divided by 3. The power divided by the root. And now just distribute that through. And so 2 squared is 4. And x squared is x. 4x squared. X squared is x squared. 4x squared. That's how we would do that. Now, an interesting thing here, this is sort of an introduction or a segue into what we're going to do in one of the next videos, rational exponents. Okay, so if you want to just keep in mind what we did here, the power divided by the root. That's the essence of what we'll look at in rational exponents in a later video. So I'm going to pause this and we're going to look at one more thing. What I have on the board are a few of the basic perfect square roots. Perfect roots. So the square root of 1 is plus or minus 1. The square root of 4 is plus or minus 2. The square root of 9 is plus or minus 3. And the square root of 16 equals plus or minus 4. Now, these are perfect squares. But suppose that you were asked to take the radical of a non-perfect square. Let's just say, just for sake of argument, something like the square root of 3. Now, you could always do that on the calculator, but is there a way that you could estimate it? And the answer is yes. And it would follow the same pattern of succession here. So basically, since 3 would fit between 1 and 4, the perfect squares of 1 and 4, its solution would also fall between the solutions of the square root of 1 and the square root of 4. So if you were asked to estimate the square root of 3, since it falls between 1 and 4, then its answer would be something like plus or minus 1.5. Because 1.5 is between 1 and 2. And following that, let's say you were asked to evaluate something like the square root of 11. What perfect squares does 11 fall between? It falls between 9 and 16, because 9 is the perfect square, which equals plus or minus 3, and 16 is the perfect square that equals plus or minus 4. So if we were to evaluate the square root of 11, because it falls between 9 and 16, then you would estimate that the answer equals somewhere between 3 and 4, and if we were to estimate, it would be about 3.2, 3.3, 3.4. Estimating, it doesn't have to be exact. You could check the exact number by doing it in the calculator. So anyway, that concludes this video. In the next video, we're going to take it to the next step in regards to radicals, and I'll see you in the next video.